introduction. Yeah, I'm really very happy to be here. And as Maxim said, I always had interest in the Russian literature. And so, but I'm not going to talk anything about Russian literature today because I'm sure you know more than me, So, but and I mean, all of us has called two sides of life. I call it livelihood and life. So my livelihood, of course, econometrics, but my life revolves around mostly art and literature. Because when I was too young, in high school, I wanted to do history and literature. My father said, no, you can be a very bad teacher, but you can never be a bad writer. Okay? So he said, no, just do science. There will be some job after you finish. So I was forced to do science, kind of physics, mathematics, and statistics. And then eventually I, transferred into, again I found out that there are not many jobs in physics and mathematics. So in between somewhere I, switched to econometrics. In fact, that's at ANU where I started doing econometrics. But now, in fact, I started teaching after my high school in different places, like a primary school and all those things. So I've been teaching, you won't believe how many years, 41 years. Yeah, so, and now I think I have done enough teaching. So now I'm going back to my, old interest, history and literature. So that's the, my second life. And I have been doing quite a bit, and I've been working on an Indian poet called Rabindranath Tagore. And again, he had a very close connection with, Boris Pasternak. And so that is my, another connection with Boris Pasternak because he translated a lot of poems of Tagore. And also there is another connection. When Boris Pasternak was in big trouble, as you know, all of you, and I think after he got the Nobel Prize, the Soviet authority wanted to kind of send him to exile. And then, of course, there was a big protest all over. And personally, the Indian Prime Minister, Jawaharlal Nehru, called Khrushchev that, if Pasternak has been sent to exile, that will be kind of, end of relationship between India and Russia or Soviet Union. And of course, Russia could not afford to do that. That time India was, biggest importer of Russian military things like all those MiGs. In fact, I visited those places where all those tanks and MiGs and those, missiles were produced and sent to India. So there is a lot of connection. So I think Boris Pasternak always grateful to India that, he was not sent to exile because of intervention of Indian Prime Minister Jawaharlal Nehru. So there's a lot of connection I can find, for coming to Russia and enjoying. And I'm just looking at first hand, I have reading Tolstoy and all those things. Now I can see, first hand how things are. Okay, so I don't have to believe, I do read called Soviet Land. I don't know, you have seen these magazines. If you can get to the library, it's called Soviet Land. And these magazines are printed in 60s in nice color paper, very nice paper, and with the beautiful pictures. And saying, how everything is perfect, like there was no unemployment, there is no poor people, everybody was happy. And, and I had a kind of, impression that, if there is a paradise on earth, that must be the Soviet Union. So that time I wanted to see Soviet Union. And also I spent a lot of time protesting USA policy in Vietnam. So, in one hand I thought, Russia is the perfect country, or Soviet Union is the perfect country, and USA is the kind of, in the axis of evil. But it's quite ironic that, now I've been living in the United States for the last 30 years. So life can be quite, ironic in that sense. Okay, so let me get into this quickly, the topic that it will be called spatial econometrics. Do you have kind of, sometime, I use, do you have that here? No. Pen and pen, oh, no. That's fine, I can still manage, Yeah, I can manage with that. Okay, yeah. So I'll be talking about spatial econometrics, and I found out that, spatial econometrics in some sense not so familiar. even in United States, because if you look at any textbook in econometrics, you won't find, forget about a chapter, even a section on spatial econometrics. There will be chapters or there will be full books called time series econometrics. Okay? And if you think about econometrics, the two main problems we deal with, say, dependence and heterogeneity. Okay, and we understand time series dependence very well, because people have been working on it. There have been a lot of applications, particularly in the financial econometrics, with different kinds of data from yearly to monthly to weekly to daily to minute by minute. So the time series econometrics is a very well developed field. Okay, and spatial econometrics, I think it was more of the field of the geographers. Okay, not I won't say spatial econometrics, called spatial analysis. Okay, and again, as you can imagine, geography. I have simple way of defining geography. My primary school teacher used to define geography and history this way. History and geography is about maps, and history about chaps. Chaps means people. Okay, so and all those, if you look at this early spatial analysis, it is all about maps. Okay, they really didn't have any quantitative, analysis, just like, drawing a map with different maybe color when the color maps are available. Okay, and so they started working on this, spatial analysis, and in econometrics, I think only recently, maybe last 10 years, it has become a little bit popular. But what has been done, it has not yet found the way to the textbook of econometrics. So that's what when I'm going to talk about it, I kind of go a little bit of history, then come to my main topic that you have seen in the seminar title, testing panel spatial model. Okay, again testing, I can say that have been my livelihood. Okay, like what Maxime was talking about, the test that I did, this Bera test, and that was my first paper. Very first paper I did, that was done 1979, many years back, and it was somehow got quickly published in a small journal, economics letters. Okay, I never thought anybody will read this paper, because it's just too simple. Okay, so that's why we decided to send it the most simplest journal, economics letters. Again, I said, the life can be very ironic, and that's the paper somehow became, I think that paper has more citation than the other 100 papers have written all combined. Okay, so you never know, what is important, Okay, so I have been doing testing, since then. And so I'll talk about testing, but before that, maybe I'll give you a kind of a quick, what I call helicopter tour of spatial analysis. Okay, now before that, sometime, we know time series is important. Capturing time dependence, is very important for in econometrics or time series data analysis. Okay, and sometimes people ask me, why this spatial econometrics is important. Okay, I'm going to tell you a story from which this line came, and I don't know about this. Who said this line? In the beginning. This is a true story. I was going to Canada to attend a conference on spatial econometrics. Then when I was about to cross the the immigration line, then this guy in the immigration officer asked me, why you are in Canada? I said, no, I'm going to a conference. Then what conference? So I pulled out my piece of paper, the conference program, telling him, look, this is the conference on spatial econometrics, and I am a speaker. Then this guy looks at very carefully, he said, but what is spatial econometrics? I was about to say, that's none of your business, I mean, you look at, but I didn't say that, I always know that, you never argue with the immigration officer. Okay, so then he himself volunteers, he has done a lot of econometrics because he has done his undergraduate degree in the University of Chicago, and he has been taught by Nobel laureates. So he said, he knows everything about econometrics, but he never heard about the spatial econometrics. I said, no, maybe it's a new subject. I also didn't know about it, few years back. Then he said, he said, no, what it is all about? No, I said it is all about space. No, he says, space, Of course, by space he meant, something up there, I said, yeah, it could be main there, also it could be, space could be on the, in this level also, and he didn't, Then again he kept on saying, he has his degree from University of Chicago, of course, which is on the top school. Then I want to, so okay, you are from Chicago, oh, I teach in University of Illinois, which is just few miles, 100 miles south of Chicago University, but that didn't work at all, it was counterproductive, Basically, he thought it is insulting to compare, my university, University of Illinois, with the University of Chicago, and he got more, kind of, little bit, I wouldn't say arrogant, but, now he demanded more answer. He said, no, I have to explain to him what is, why this special thing is important. And it went on and on. They said, no, after a while, no, there is a long queue. People are getting very impatient. He said, no, you have to tell me in one line. No, so that he can understand. So I am not sure. I said, no, if I don't do that, what will happen? He said, no, then you are not getting into this country. Then I have to come up with a very simple line so that, he will be happy. Then, suddenly, somehow this line appeared to me, that without space, we are nowhere. And this has nothing to do with econometrics, this is like a general comment. And somehow he liked this line so much. He said, no, yeah. Now he said, he understood why it is important. He said, now you can go enter the country. Okay. So this line, so anytime, something happens like this, you can use it. Okay. So sometimes tell this story whenever I give a talk on, on spatial econometrics. Okay. Now let me see what I. Pointing. Okay. Yeah. So I can use this. Yeah. No problem. Yeah. Okay. Oh yeah. Okay. So maybe I don't know how much I will get into the testing. Let me talk about start with testing. Okay. People call it testing, but I said no. These two things are very highly related. Testing and I don't know how to pronounce. English is not my first language, but when I say they sound the same. Testing and tasting. Yeah. Okay. Okay. See, when we do the model test econometrics, we see how bad it is. But if you look at the wine testing, tea testing, you see what how good it is. But they're very similar thing. You are evaluating certain things. Okay. And again, this is the kind of I use in my teaching. I say the first statistician I met is my mother, who never went to school. Okay. But she was I call sampling theorist or sampling statistician. And I mean, you have seen this, your mother or you do this. We had a big family, 7 brothers, 2 sisters, and she used to cook huge amount of rice. And I would see, to check the rice, of course, she will take only teaspoon of rice, which will be little sample of the huge rice, and then put in her finger and see whether it is cooked or not. And if that is cooked, she said, okay, it's done. But I never believe this, doing this in your hand, I mean, no, you are not going to, your hand is not going to eat, you are going to eat your mouth. So I will leave either, no, give me, I want to see it how cooked, So I would go a little bit, one more extra step, do the real testing, by eating, not just by hand, okay. So that is the kind of, I say, and I give a picture of my mother who passed away, just 2 years back, and this is my mother cooking back in India. And you can imagine, my village, it does not still have electricity. So it's a remote Indian village, and you can see that, sometimes I give this to my students just to get an idea, not about econometrics, but the sociology. So here is my mother cooking, and if you look at the oven is like, something just dig into the ground, okay? And the fuels are here, the twigs and leaves of the trees. And look at her gadgets, that's all she has, a bucket of water and some oil and some spices, that's it. And I complained to my wife, with these simple things, what my mother used to cook, my wife is still not replicated even with 60 more gadgets, okay, so you don't need to have, gadgets too. Okay, so here is my mother cooking, and here I say my mother is the statistician mother, okay, testing the rice. Okay, so this photo was taken just before she passed away, when she was like 91 or so. Okay, so that's why I call my mother is, sampling and testing. Okay, so we'll talk about this testing. Okay, and it has some relevance in some way. Okay, now what happened, sometimes my mother would go a little bit, further, even do anything. She will put the rice, and then after some time, rice is done. Won't bother to check. Then I found out, basically she will put the right amount of water. When the water is dried up, she said, okay, my rice is cooked. Okay, and that's kind of the simplest way of, coming to the conclusion, even without touching the rice. Okay, but only thing you have to be careful, in this context, you have to use the, kind of right amount of water, to come to the conclusion. Okay, so in some sense, as you can see, as you know, when you know econometric testing, there are many ways of doing econometrics test, and this called Rao's code test and this is the most familiar one, likelihood ratio test. In likelihood ratio test, what? You have to have estimate both under the null and also under the alternative. Okay, and then you look at the how the two things differ. That's the likelihood ratio test. And wall test, basically you look at the behavior of your data or model under the alternative, how does it differ from the null. Now, as you know, in the Rao's code test, what is also known as, in literature econometrics, we call it LM test. Okay, so most of the, if you look at in econometric textbook, they will call it an LM test, and statistics textbook they'll call it Rao's code test. Okay, and as you know, Rao's code test, what you do, you essentially don't need to estimate the model under the alternative. The whole idea of the Rao's code test is based on the score function only under the null. Okay, I'll come back to that, But again, you are testing the same hypothesis in 3 different ways, and most of the time, you reach the same conclusion. Okay, so when I call testing, this testing is more like this likelihood ratio test. I mean, you take the maximum effort. Okay, okay. Now let me do a kind of very simple basic math and stat 101 that we do all the time, because sometimes I have seen some people are commenting some textbook that this is the best thing if you can do it. If you can estimate the model under the alternative, then you should do this, because since the Rao's code test, it does not use the full information in the sense of your alternative hypothesis, maybe you are losing some information. Okay. And so, so sometimes people still use the likelihood ratio test. Okay, but what I'm going to tell you, I mean, even with the Rao's code test, you can kind of extract as much information as it is possible that you can get from the full-fledged likelihood ratio test. Okay, I mean, let me give you the example that most of you use while teaching, a stat 101. Okay. Suppose we want to test this simple thing. I call it this most simplest model we can think about. Okay, and I want to test this, and then we know with the Neyman Pearson lemma, the uniformly most powerful test is based on the minimal sufficient statistic, the sample mean. Okay, we know sample mean is the kind of it has all the information about the population mean. Okay, and so if I write down the likelihood ratio test, so this one will be the log likelihood function for this simple model. Okay, and then likelihood ratio test will be you estimate mu hat. Then of course here under the null there is no estimation involved, because under the null mu is 0. So you look at the difference between the likelihood ratio likelihood function under the alternative and under the null. And sometimes if there is a unknown parameter under the null, then you put call say mu tilde. That will be unrestricted MLE. Okay, so and here when I put mu is equal to 0, then of course this will be just summation of yi square, and then as you can see that this what will be left with just y bar square. So this is the likelihood ratio test. Okay, so it is based on the sample mean. Okay, so but again in this simple situation, or if you think of a complex situation, you have to estimate the model under the alternative, means when mu not equal to 0, and you have to estimate the model under the null, if there is unknown parameters under the null, and then look at the difference. Okay, because we know if null is true, mu hat should be close to the say is equal to 0. Okay, so okay, I mean this is a kind of just repeating what generally the way you teach the students. Okay. Okay, now let us look at this way. Okay, Okay. Let us look at the score function. As I said, no, score function is simply the derivative of the log likelihood function with respect to the parameter. Then you evaluate the score function d mu at say mu is equal to 0. Then what you see, you get back the same thing, no, sample mean. Okay. So what I said, no, so what is d mu? Basically what you do, no, you take the derivative of this, with respect to mu, and that gives you this quantity, and when you put mu is equal to 0, we end up with this. So the score test will be also based on the same quantity as the likelihood ratio test is based on. And now if you look at, there is absolutely no estimation here, absolutely no estimation, okay, but it end up with the same thing, okay. And so that means, that this has same information as we have seen in the likelihood ratio test, okay. And so that's why, in some sense, look at, we are not estimating mu, but somehow the score function is directly a function of the mu hat. So indirectly it will give you estimate of the parameter, although there is no estimation involved, okay. So this is the kind of simplest case like this, okay, simplest case like this, but generally this holds true. Even more complicated cases, we will see that the score function will be, in most cases, will be minimal sufficient statistic. Okay, so you are not estimating directly, but indirectly are estimating without putting any effort. Okay, now let me do this kind of geometrically. Then you can think about this. Okay, what is the likelihood ratio test? Is basically this quantity we said. Okay, let me plot say mu this side, and this is the score function, d mu. You cannot see it, but this is d mu. Okay. Now, if I how can I get the likelihood? I can kind of integrate the derivative, then I can get back to this this one. Okay. So if I integrate this derivative score function from 0 to mu hat, this will give me this. Okay. And what is this quantity? In the picture, I am drawing, plotting d mu against mu. So this will be just the area under the curve from 0 to mu hat, 0 to mu hat. And what will be this? This will be just this area, under this, area of the triangle. So the likelihood ratio test will be just the 2 is there, of course, under this triangle. So that's my likelihood ratio test. Okay. Now what we said, what will be the score test? The score test, what we are saying, so here is called my mu is equal to 0, and here my mu is equal to mu hat, because what is mu hat? The value of mu where d mu is equal to 0. So this will be the mu hat. Okay, this will be the mu hat. Okay. Okay. Now what we said of the score test we said the value of the score function at mu is equal to 0. So the score test will be just this length, is it not? This length. Okay, and we already saw this is basically ny bar, this length. Now you can see that the connection between likelihood ratio test and the score test. Okay, the likelihood ratio test is area of this angle essentially, and score test is basically the length of this d mu at 0. I have not seen any textbook talking about this, but I think this explains the difference between the likelihood ratio test and the score test. Okay. Now as you can see, they are kind of not directly proportional. That if the area of this triangle come to 0, then this d mu has to be close to 0. Okay. So you are essentially doing exactly the same thing, but you don't have to solve that this d mu, the first derivative 0 at certain point. You don't need this information at all. You can just kind of try to see how close to 0 this quantity. So this is my mu hat, this is my mu is equal to mu 0. So under null is true, then this distance should be close to 0. Again, if this distance is close to 0, then this has to be close to 0, or if you think about likelihood ratio test, the area has to be close to 0. So they are essentially identical. But here, as I said, for the normal case, the score function is a linear function, is a linear function. So that's what I could draw very simple like linear function. Okay. Now in a general case, what will happen? No, it will be not be linear function. No, it may be somewhat non-linear. Now think about a non-linear function. No, it will be like this. Then what will happen? If it is non-linear, your likelihood ratio test will be just the area under this non-linear curve. Okay, but nothing will change of the score function. No, it will be still the same thing. Again, area under the curve will be close to 0 if this vertical line is close to 0. Okay, so it won't be exactly directly proportional, but it will be approximately the same. Okay. Okay, so you can think about that there is no need to estimate the full model while you are testing. Okay, I'm not saying the likelihood ratio test is redundant. No, if you want to have a easy way of doing testing, there is no need to estimate the model. And also, see, when we estimate a huge model, but nowadays it's not very difficult. No, there's a computer, there's a package, you can estimate anything. But the question is, the numbers you get back, estimating a huge model, those may be unstable. No, think about like in the finance, they use this huge, multivariate GARCH model with say 10 markets, or sometimes they do more. I mean, there are kind of, hundreds of parameters. And once you estimate the 100 of parameters, of course you get a number back once you put the data, what those number, what are the stability properties of those, parameters, we don't know. So that's why I always try to, but it has not been, people are still very skeptical about it. But my idea is, if you want to test a model, okay, start with a general model, but do not estimate the general model. Estimate the model under the null and see which way we need to go further. No, because you might want to look at many directions, but all the directions may not be important for your data. So you test the model, see what if anything is wrong. Then if something is wrong, then you look into very specific direction that where the model is not valid. Then you make a correction or adjustment only along this direction. Okay, I'll further elaborate that. Okay, and you can ask me any questions anytime. So as we go along. Okay. Okay, so that's what I was kind of talking about, a test is like essentially a distance measure. So likelihood ratio is essentially looking at the distance between mu hat and mu through the log likelihood function. And score test what is doing, it is looking at the distance through the score function. And we know by definition of, so this, if mu is close to mu 0, then d mu hat should be close to d mu 0, but by construction d mu hat is 0, because this is the MLE, and MLE has the first derivative 0. That means all you need to do, just look at this quantity, because by construction this is 0, so all you need to look at this. Now, as we have said, that this particular quantity gives a, of course you have to, what we call, normalize, with the variance, but this is the main quantity. What this core function at mu 0, what it gives you a measure how far you are away from the null, just like this, what I said, the measure of, distance from the null, I said this gives you, indirectly the measure of the distance from the null in this simple one parameter case. But if there are many parameters, the same idea applies, okay. So I said, get this quantity, okay. There could be many parameters, here I am testing one parameter, but you might be testing many parameters. Okay, then this will give you what I call, how far you are away from the null hypothesis. Okay, and that's the kind of, say let us call basic model is null. Then this is what I call, the amount of say misspecification. Okay, and if there are many parameters, that means you are looking at the misspecification in many directions. Okay, so once you get the total, amount of misspecification, then you can decompose, which direction the misspecification is. Just I said, in econometrics we do talk about, say you have panel data, you have a basic panel linear model, then how it can be misspecified. Maybe there is a heterogeneity through random effect or fixed effect, or there may be a serial correlation in terms of time series, okay, or you might have some called dynamics, like a dynamic panel model, that means your yt depends on yt minus 1, or you might have not linearity, we might have non-linearity. So your model can be different from the basic linear model in many ways, okay. And the idea is, but estimate the basic model, simple linear model with say OLS. Get the total measure of misspecification. Then decompose the total measure of misspecification, see which direction that is significant. But again, when you decompose, you want to decompose in such a way that those are kind of orthogonal, just like we do the analysis of variance. See, what is analysis of variance? You have the total variance, okay, what you call total sum of square. Then what we do in whole regression analysis, basically decomposing this total variance or variability of y into two components. One we call the regression sum of square, one we call the error sum of square. What is the good thing about this? These two components are orthogonal. That's why this decomposition valid. If they are not orthogonal, they are not a decomposition. Okay, that's what I call. Basically, it is going back to 300 BC Pythagoras. Basically, what Pythagoras says, you can decompose something into two orthogonal parts. Okay, so if I have two parameters, what I will do, I look at the total misspecification, that will be my this, what you call that, other part, and then you are decomposing into, say called a square is equal to b square plus c square, and your b and c are orthogonal, if that relationship hold. Okay, we will come back to that. Okay, so this is the kind of main idea. Okay, so that's what I said. Think about in econometrics. This is the basic. We start with econometrics 101. We said we start with this model. Okay, and we can estimate it. Okay, now what you call what kind of departures we should be interested in. Okay, from this basic model. Okay, basically we are asking the question: what is a misspecified model, or how this can be misspecified? Okay, and I mean, as you can see, there are a lot of assumptions are embedded in it. We said UIs are independently, identically distributed. Again, what kind of distribution? Normal distribution. Then you have the same variance. The homoscedasticity come to the picture. Then you say this is a linear function. Then you say X are exogenous. That means they are uncorrelated. There are many assumptions embedded into this simple structure. Okay. So if you have to answer the question, what is a misspecified model, is very difficult. So when you have a when you face a difficult question, what do you do? Then you can go back to your guru. Of course, you know him. Okay. So I use a lot of quotation from Tolstoy in my class. I said he is the greatest econometrician. Okay. So in the context of misspecification, I said, now what is misspecified model? Okay, and of course you have seen this many times. Just paraphrase Tolstoy, you get this. Okay, so when a model is right, it is right, but if it is wrong, it is difficult to say which way it could be wrong. There are many ways. Like when a family is unhappy, it could be unhappy in so many ways. Maybe husband is seeing another woman, or the boys are not having good grades. I mean, many things can happen. It's very difficult to tell, specifically, and each is basically quite different. But so that's why you have to be very careful when you talk about misspecification. Okay, so that means we cannot take care of everything. We have to think about very specific things. So this is what I will be talking about. In the so that's my title of my talk. You have this basic panel model. Okay. Now again we say what can go wrong with this model? Just we can again do the Tolstoy. Basically, almost everything can go wrong with this model. Okay. In fact, no matter how much effort you put in your model, all models are misspecified. Okay, but some models are useful, even they are misspecified, and that's what we're trying to get. Okay. Okay. So we can kind of talk about only limited number of departures. Okay. So in this context, okay, yeah. So I basically at the end, this is the model I'll get into. This panel, basic model, and then we'll see what are the departures we should be interested in. Okay, so I'll talk about this is called standard, the most basic say panel linear model, and then we talk about, now you can kind of, so this is like a panel model with n individuals, or it could be n countries, or it could be n location, or in the finance context, this n could be like, number of, say, markets or stocks you are looking at. No, okay. In spatial context, people kind of misunderstand. Now, it must be a geographic location. No, this n could be anything, and it could be n individuals. No, it could be n individuals, like students in a class. Okay, and this is the time. Now you can have dependence through this location, or through time, or sometimes you could have interaction between the space and time. Okay, or you might have a lagged, a variable here. You might have dynamic models, and so many things can go wrong. Okay, so we'll come back to this. Okay, so but sometime I want to do, but I like history, so sometime I want to go back to kind of the what I call the genesis of spatial analysis. So what I call the capsule summary. Okay, okay. So sometimes try to give it like a little bit attractive or funny title so that people will remember this. What I call spatial analysis in time of cholera. Most of you have read the book Lab in Time of Cholera. So but I have a call spatial analysis in time of cholera to crime in Columbus. Okay, it most looks like a title of Dostoevsky novel, Crime in Columbus. No, I'm not that good, So, pardon?
No, but like, where does it come from? The second part, the crime in Columbus.
Oh, Columbus. Oh, we'll get to this. Yeah. So we'll start here. It is more like giving a very simple survey. Okay, so we'll cover this almost 150 years. Or more than that, maybe 200 years we'll cover. So I call it a capsule summary. Yeah, we'll come to Columbus. Again, crime in Columbus, if you want to go study in crime, I think United States is the best place. Now, there are lots of crime, that means there are a lot of good data on crime. Okay, so that's what I say, it's a very good place, to study crime.
Where is it?
Pardon?
Where is it?
Oh, Columbus, it is Ohio. So it is the, Ohio State University. Yeah, that's Columbus, yeah. I use it just because it sounds nice, crime in Columbus, Yeah, because of that. Otherwise, I would have taken, any other city, Crime in New York does not sound as good as this one, so I thought, Okay, maybe I want to do too much. Let me just only concentrate on this one. So as I said, I looked into a lot of books, but I have not seen any, spatial analysis book talking about this part. I call it ghost map. Okay, so this how many years? 150 years. Yeah. Okay, so let us go to this one. Okay, so let me see what happened. Oh, these are the kind of you want to know about, spatial analysis. This is what I call Bible. And there is a new book came out a few years back, and there is a handbook which came this one, and this came out essentially last year. So these are the kind of the books that I could think about in spatial analysis. Okay, and this book is still kind of considered to be the Bible of the spatial. It is nothing to do with econometrics. This is more pure statistics. This is a pure statistics book. By Newell Cressy. Okay, and in fact he is in Columbus, Ohio State University. So, okay, so this is a what do you call this is the tube well. I don't know you have tube well in Pittsburgh anymore. It must have been there last century or before that. Okay, but yeah, this is the kind of only good source of clean water. Long time back, before the pipe water came, and this is, I saw the picture in a book of this, tube well, but can you see something unusual about the tube well? You can see that. See, tube well, you have to pump the water, Exactly, it does not have the lever, right? Exactly, and I didn't believe it, so I went all the way to place and took this picture in August 20 or 25th. Okay, so this is a real picture, okay. So what I will be saying here, everything is truth, nothing but the truth, So I want to make sure, Okay, but what happened to this pump? Okay, there is a big story. That's what I call, spatial analysis in time of cholera. It started, this 1954, Monday, 6 a.m. And these are all recorded information. Okay, I'll tell you where did I get this all the information. And this is near the Piccadilly Circus. There is a street that the pump you just saw. This is on the 40 Broad Street, and there was a apartment building, 3-story apartment building, and in the apartment building there is a family called Lewis family. They used to live in this in the basement, and their 5-month-old daughter had started having this diarrhea or cholera, and I think the symptoms of cholera, so I don't have to go into details. I don't want to destroy your appetite for dinner. Yeah, so let us forget about. Okay. So that was on Monday, and then see, this is a street. I don't have to imagine how it look like, because in Calcutta we still have, we are maintaining the British tradition. You will have a street, we still have pump, and then how the way, if you have been to Calcutta, you will see there will be 2 drains in the 2 sides of the street. Okay, they're all open drain, and if you want to get rid of anything, you just throw it into the drain. Okay, and so this Mrs. Lewis will clean the diapers of this girl, all those dirty diapers, and put all those water into the drain in front of the house. Okay, and during those days, of course, they didn't have this disposable diapers, so they had only cloth diapers, which was kind of environmentally, of course, friendly, but again, you can guess, they have to be clean, and then she will put all the clean water, all the dirty water into the drain just in front of the house. Okay, so there was a drain flowing in front of the house, and there was this, water pump. And water pump is, I call it, almost like a social institution where people will gather, not only collect water, but also exchange all the neighborhood stories and gossips. Okay, so people will be coming there all the time. And also next to the pump, there was also a called pub. Of course, the pubs are very popular in England, and it was very popular even in those days. And near their house, there was a a beer factory with 535 inmates. Okay, I don't know whether you know about this workhouse. If you have read Charles Dickens novel like David Copperfield, you will get a first hand, because he himself spent quite a bit of time in this workhouses. If you cannot pay back a loan, then you are sent there and work almost like a slave. And of course he didn't take any loan, but his father took a loan, couldn't pay it, so he had to go there. Okay, so this is the workhouse there are lots of workhouses during that time in London. Okay, so and sometimes people will think these are the very poor people, and if anything bad happens like a disease or anything, they will be the first group of people will be affected because they are not rich, or they don't keep themselves healthy, or so that was the kind of belief during that time. Okay, so they usually very close by. I'll show you the map. Okay, so it started in 28th Monday, and then Tuesday what happened, the little girl condition didn't improve, and the following date, after August 30th, as I said, the Lewis family live in the basement, and on the first floor there is another family called Taylor family. The Mr. Taylor started having a symptom, and he died the next day, Friday. Okay, and the little girl died on Saturday. Okay, so this all happened in the same building, but somebody else died quite far away called Sujani Eli, and these names are all real names. Okay, and which is a little bit further north. Okay, and that means within a week they had a full-fledged cholera outbreak in that particular area, near the Piccadilly Circus area. Okay, I mean you might be very familiar with that area. Okay. And then on next Monday, now we are more than a week, little more than a week. The Taylor wife, they didn't have any children, so the wife got sick and then she died, after a few days. Okay, then ultimately Mr. Lewis got sick. Okay, Mr. got sick, but nothing happened to Mrs. Lewis. Absolutely nothing. She survived. Okay, but when her husband got sick, of course, she continued doing the same thing, washing the clothes, throwing the water into the drain, you know, in front of the house. Okay. Okay. But of course, you know, the city didn't, you know, stay idle, because, you know, that time they used to think that cholera is a disease of the, you know, third world countries. Okay. And so they are kind of taken back, you know, with this outbreak, you know, at the heart of the London. So city took all the action that is possible. No, they had plenty of money, no, maybe from India, no, there are a lot of money there. So what they did, you know, that time the whole theory of cholera was that, you know, that cholera is a airborne disease. That means, you know, it passes through, you know, air. So they said, no, you must have a fresh air, you know, to prevent, you know, cholera further. So they clean all the streets, told the people stay inside, close your windows, also doors, you know, and they took all the precautions, you know, and I saw a lot of beautiful pictures of the street, neat and clean, you know, almost like your drawing room. Okay, but that didn't prevent, you know, spread of the cholera. Okay, and then, you know, the husband of Mrs. Lewis died, you know, as I said, no. Okay, and within 2 weeks, you know, basically around 600 people died. Okay, you know, in that, you know, called Golden Square area, you know, near Piccadilly Circus. But quite surprisingly, these, you know, poor people work in the workhouse, nothing happened to them. They all survived. Okay, so there was a kind of, you know, so city will every day they will publish, you know, details, who got infected and, you know, who died, you know, with their, you know, names, age, everything, you know. And there have a lot of people have been working, you know. There is a very famous statistician, he is called the father of official statistics. So he got into there and he was in charge of publishing all those, you know, statistics every day. So the Times of London will have all the details, you know, of, you know. So that's why the names are there, you know. And they also will have city council meetings, emergency city council meetings, and they will discuss it, and the minutes of the meeting are also available. Okay, so they will discuss. Okay. So there was a big.
So this is how they got to know that everything started from the Lewis family.
Oh, not yet, not yet, not yet. No. Okay, no. See.
I mean, in the first place, how did they know that it all started with the baby in Lewis?
No. I mean, when that happened, no, nobody cared about it. Right. First week, there's absolutely nothing. They didn't know. They said no, because the Lewis family was not a rich or anything, so they didn't pay any attention. And when the kind of, after first week only they started, taking kind of action. So I don't think they pinpointed Lewis family that time yet. Okay. Yeah. So kind of, second week they started publishing these things, Yeah. The Lewis family came little later. I mean, the connection to the Lewis family. Yeah. We will get into that one. Yeah, exactly. But that time they didn't know. No. Yeah. Yeah. That's a good question. If you look at the newspaper, first 3 days the newspaper didn't even mention about this because the people are dying, poor people, No, that was not in the news, Yeah, that was not in the news. But second week they started doing this cleaning and everything, and then all those, politicians visiting the place. Then they employed a statistician to keep track of, how many people dying. Okay. Then somebody comes in this picture, what I call Dr. John Snow. And he was not a medical doctor, but what is called, he was the first anesthesiologist of Britain. I think anesthesiology just started that time in the United States, just started. And he was the first person to kind of, get into this technique, because even during that time, if you have to have a surgery, people won't have any anesthetic, they want to do something in your hand, they will just chop it off. Okay, or want to extract a teeth, they just take it out, So he started, doing this. And one thing also, not only did this, in the United States, of course, it was there, but they didn't know how much, this chloroform to be given to people. And many times, they will give a amount which was just too much. So they will have a successful operation, but the patient won't come back to life. And sometimes they will be less and the patient will be screaming, during this. So neither was good. And what Dr. John Snow did, he experimented on himself, trying to find out the right dose. that this operation suppose takes 2 hours, then he will say it needs this much. And he will experiment himself, after how long he will come back to sense. Okay, and that's why you can see that he died very early, because he contracted a lot of disease because of his body was just like they say it was full of chemicals when he passed away. Okay, but it has a lot of influence in Britain. So when they found out that this is good, and first person to benefit out of his experiments is Queen Victoria. She had 6 children, and these last 2 were born with chloroform. Of course, she has to fast, And when it was successful, this guy, Dr. Snow became very, very famous, because if Queen has a faith on him, that means, general public should have, And I think if you think about who this person is, Prince Leopold, who became the king, and he is, I think, great grandfather of the King's Speech. Okay, so you can connect this guy, Okay, so this is okay, and also he's a good friend of. So then he was able to move, among to the elite group of people like writers like Jonathan Swift and so he was in a good position, Dr. Snow. Although he was not kind of very, person that looked for publicity, because he never married, all the time bachelor, vegetarian, never drank, complete teetotaler, and lived alone. And I think with his brother he lived alone. Okay, yeah. So, and it's quite an unusual kind of person, Yeah, and that Dr. George Snow. Okay, and I like this picture for one reason, because one day my daughter saw this picture. My wife, a 12-year-old daughter, she saw this picture and suddenly she said, "My God, Dad, why you in such a good, dress up, Okay, she thought this is my picture. I take that as a big compliment. Yeah, okay, yeah. So this is Dr. John Snow. Okay, what Dr. Snow did, he had the same information, all the numbers of deaths, when did they die, but okay. So this is that area we are talking about. So here is the Piccadilly Circus, and this is the Broad Street. See, this is called Broad Street. And these are the kind of water pumps in different locations, and this is the famous Oxford Street, where you go for your shopping, and these are the kind of all crosses are I think there are around 12 pumps in that area, and this is exactly the map Dr. Snow did, and this is the Broad Street, and here is this pump, this is the pump, and this is the building, and I think ultimately 5 people died in that building, okay, and here is the pub, okay, and here is the workhouse. It's a huge workhouse, but nobody died there, okay. And as I said, also this lady died, Susanna Ely in Hampstead. She's like 4 miles north of this place, okay. So what Dr. Snow did, he had the data, but along with the number of people died, who died, he, as you can see from the map, he wanted to know where did they die, which location they died. He got their addresses, put those things. Then he went to each and every house, okay, asked them about this, As soon as, it doesn't require any, genius to find out that all the deaths are clustered around this pump. Okay, as I said, the pump is also close to this, Lewis family, next door. Okay, he said there must be a connection, with this pump and with this death. Anybody can say that, they're all clustered, and that's what we ultimately will call, the spatial dependence. Okay, I think any dependence is essentially a cluster, no matter what. Dependence means, you kind of bunch together. Okay. Okay, I'll come back to clustering a little bit more, Okay. And then he went each and every house and asking them, did they drink water from this pump? And when did they drink? And what happened to these people? Did they contract the disease? And he found out whoever drank the water got sick, and many of them died. And this lady who was living somewhere further north, she used to live, close by, but then she moved out very recently, few days back. But she always liked the water from this pump, because the pump water is very tasty. And Dr. Snow again writes somewhere, he claimed that the water of the pump is contaminated. That's why it was also, tasting pretty good. Okay, I tell my students, if something tastes very good, be careful. It may not be good for your health, Okay, so that's what, in some sense, we try to do a lot of experimental economics, before and after, or treatment effect. Now almost, he set up a natural experiment here. He went after the fact, he went each and every house, collected the data, found out whoever drank water, and then they got sick and died. Okay, that proved one side. Now the question is, suppose somebody didn't drink water, what happened? You don't have the data on those. But again, when he didn't have data, but of course he cannot go to a visited place where nobody died, but he had this information from here. He found out that nobody died here. All those poor people, all those unhealthy people survived. Okay, because what happened, those inmates, they didn't have enough food, of course, and they didn't drink water. What they did, they drank just the beer, whatever they produced. Okay, and they survived. And sometimes I say, beer is good for you. Okay, yeah, beer was very good for them, Okay, so that was his whole idea. That he said water was, and in fact what he did, he looked into the, he asked the city to dig it around the pump, see what happened to the pump pipe. This pipe goes around 150 feet, but after 50 feet, there's supposed to be a kind of wall between the drain and the pump, but that wall was broken. So all the drainage water that Mrs. Lewis is now throwing into this drain, some of them, sweeping under the ground, and people are essentially pumping out, that, contaminated water. Yeah.
I just missed it.
Yeah.
Why did the Mrs. Lewis didn't why did
Exactly right. That's another point, She didn't drink any water of the pump. She was so busy, she's taking care of their, first for that, and then, she didn't drink water from that particular, I don't know. See, some people like it because it is, tasty. Right. Yeah, somehow she didn't like that water, or at least, that's what Dr. Snow found out, And I think she drank it a little bit, but again, it's a kind of question of your immunity. I think if I forgot the numbers, 95% people, got sick. And she may be one of those 5%, She drank a little bit, but not like, whatever happened. Yeah, her husband at least, will come back from work. First thing, she has to prepare this big glass of, this water with some whatever, And that's what her husband used to do. Okay, yeah. She drank maybe not much, Yeah. So she survived. Okay, that's why she was able to tell all the story, how her daughter got, But nobody knows how the daughter got first sick very first time. We don't know. Okay. Okay, so that's what is whole idea that this. But again, this was completely opposite of the medical theory that cholera is a airborne disease. And when he said, cholera spread through water, nobody would believe it. It's like, you are talking about something. And again, he was not a medical doctor, so nobody believed him at all. So first he said, remove the pump. Of course, city won't agree with the removing the pump. Okay. And so.
And then just remove the lever.
Exactly, yeah. So city only, then he said, okay, if you don't remove the pump, just, at least, remove the handle of the pump. Okay. And then of course, what happened, the next few days, there was no new cases. So this is another extra proof that for his conjecture that this disease was spreading through water, and this pump was kind of responsible for that. And it took so many years afterwards to find out the real, I mean, you might know this is the guy who got Nobel Prize, I think first maybe, I think he got Nobel Prize 1902 for doing this one. Okay. And there is also a lot of work by Italian, because the cholera was also not, what should I say, it was not common but also not uncommon. I think in Russia you had a huge cholera epidemic in 1829 to 1831. 1829 to 1831, and there is a famous doctor, Grail, Grail. In fact, I found his statue in city of Parma. Yeah. But he didn't go up to but he tried to kind of, protect people. So there is in rural region, I don't know, thousands of people died. You might look into 1829 to 1831, and this, this doctor, he tried to save, he saved a lot of people. I think he tried to save people by not going into theory, kind of isolating them. So that there is no kind of, they won't, what you call, share, water or anything, but he didn't know about it, but he saved a lot of people, kind of moving people out of that region, so that, so that they will get, don't have, share the same, but of course he didn't know anything of the water part, yeah. So in that sense, what I say, that, so this is the kind of beginning of the end of the cholera, but again, it's the starting of a new field, you can imagine, called epidemiology. And again, what he achieved just by a piece of paper, nothing else. Of course, he did a lot of research, but his whole finding is whole summarized in this map. Okay, and sometimes people call it a ghost map. In fact, there is a book or couple of books written on this, but not by any econometrician. No, it's more like a sensational, kind of story. And there is a movie or kind of somebody had made out of this. Okay, but again, nothing to do with much with any statistics. So if you look at statistics, we don't have much of success story. If you look at physics, chemistry, there are a lot of big success story. Atom bomb or computer, TV. But in that sense, I think this Dr. Snow's discovery is no less than any of those major discovery. Because this is the kind of major success story in statistics. And I think in epidemiology, he's really recognized pretty well. I have seen a lot of books in epidemiology. They do acknowledge Dr. Snow's analysis, but I have not seen any statistics. Forget about econometrics book. Where they acknowledge Dr. Snow. But I would rather call him as the father of spatial analysis, because he is the first person to kind of see the importance of location. A spatial analysis is essentially about the location, whether location is important. Okay. Nowadays we know, like when you buy a house, first thing you look at the location of the house. That's why in US they have this kind of saying, there are three important things when you buy the house: location, location, location. Okay. So now people know about this location, importance of location.
Set up some sort of histogram at the very least to
right, exactly.
maximum density.
Right, exactly. Exactly. So in the one dimension, you can look at the histogram and you can see this, clustering. And in the plane, you can look at the histogram in 2 dimensions. Like, in a stock market, if you look at this, times, say stock returns, and we know that certain time you have, highly clustered data, too high or too low, they all clustered together, like, maybe 87, then during the Asian crisis, 97, 98, and then if you look at the last couple of years, they're all kind of high volatile. But good, if you think about this kind of puzzling, there is if you calculate the correlations of the stock price, is almost zero. There is no linear dependence. Okay, there is absolutely no linear dependence. Very little. Because of course it has to be something to do with also efficient market. The stock prices are not predictable. Okay, and if you think about the whole literature of arts, basically what they did, instead of looking at the return, just square them. As soon as you square them, basically you can now see the clustering in much better. And then you see, say your return RT is uncorrelated with RT minus 1, but RT square is very highly correlated with RT minus 1 square. So they are not linearly dependent, but they are non-linearly dependent. And that's the whole idea of the stochastic volatility model. No, that means you are not able to predict the say return, but you are able to predict the variance of the return. Okay, that means you are not able to predict the return, but you can somehow predict the risk, which is changing over time, and that's still a very good information. No, that means you can predict in some sense the market risk. Okay, so again that's same thing as what you're talking about clustering. Okay, but again I can give I don't think there is any work on that because it's still new. If you think about like stock prices, I have seen a lot of time series work, but you can predict about a particular say stock, not only looking at the stocks historical data, maybe you want to look at similar kind of stock. Say you are looking at Microsoft, then you want to look at maybe Google or or Yahoo, and I think they are related in some sense. So sometime you want to predict something, you might get a better prediction looking at the similar kind of stocks, and that I can call spatial dependence. At a particular time, these many of the similar stocks are spatially dependent. I mean, we are not talking about space as such, but cross-sectional dependence. I have not seen people taking kind of explicitly that into account while predicting or analyzing stock prices. It is possible because you can imagine that your stock prices of say IT stocks may not be related to some utility stocks, okay, but they will be closely related to similar stock. Okay, I mean it is the same theory people have done. If you want to predict the student's GPA, you do not look at only the same student record, you look at the students similar kind of student. And also I have done in my class, I said I have done this, I've done this many times. I see generally when you teach, you will see after a few weeks the students will be sitting on the same spot every day. Every day they won't change, it's like they will own a spot. Okay, then what you could do, you can look at their location of the students, then look at their score at the end of the year. You will see the scores are highly location, they will be all cluster. You will see the good students will be sitting one side, not so good students will be other side, but those who move, they are sometimes the middle type of students. They don't care where they sit, sometimes they will be moving around little bit, but the good students and the other group, other extreme group, they will be all clustered. And that's what I call a very good example of spatial dependence. Okay, or the friends. So nowadays people say that like in the if you want to improve student score, what you should do, not just give the improvement to the student, but you want to kind of put them together so that they can learn from each other. There is so it is something like called spillover effect. Okay, we will talk about that a little bit. So what is the use of learning spatial dependence? Because there is a lot of a spillover effect. That means you want to improve one region, you don't have to kind of give money to everybody. If you develop one particular spot, then other surrounding spot will get automatically improved. Okay, so that's we will talk about in the context of
I hate chasing you out.
Oh no.
I'm judging by the number of the slides left. I need to speed up.
Oh right. Oh my goodness. Oh my goodness. Okay. Yeah, you're right. Okay. Yeah. Right. Yeah. No. I don't intend to go up to page 85, of course. And we'll see how much we can go. Yeah. Oh, you're right. Oh, thank you. Yeah. Okay. Very quickly. So if you go from the palm, walk few 100 feet, you will see this pub. Okay, it's called John Snow pub. So to kind of honor Dr. John Snow, British people, they have there is no other memorial than this pub. Okay, and again I think why the pub, remember nobody died in the beer factory, so basically means as I said, beer is good for you. And in this pub, you'll see first floor is the pub. It's an unusual pub, but in the second floor you have all the material that I talked about, all the pictures, city, meeting, I mean, all the minutes of the city council meetings and everything is there, okay, in the second floor, okay. But there is a little problem. To go from the first to the second floor, you have to become a member of this pub, okay. But that's very easy. All you need, just buy a glass of beer. Then they will let you go, Okay, so I had to buy this glass of beer just to go upstairs. And you can see this is me, same shirt. Okay, so sometimes people say, no, have you really been there? No, I said, look, no, this is a sensor. Then they believe you, So search is more important than, the person. Okay, so then let me, yeah. Okay, now the first, as I said, so we are now 1854. Let us just kind of move, almost 100 years. The first person to talk about, the spatial dependence analytically, the statistician from Australia, Pat Moran. And in fact, he and I were the same department when I was doing my PhD. Okay, we were the same department. One of the, I think he's known as the father of statistics in Australia. Okay, and you might know Ted Hannan, E.J. Hannan was his student, the Times his guy. Okay, so a lot of people, Adrian Pagan was, okay, his student was called Dean Turrell, and Dean Turrell's student was Adrian Pagan. So Adrian Pagan was his, like a grand student. Okay, they're all the same, department of statistics in ANU, Australian National University. Okay, now what he did, okay, this is in his memory. I think this is better. They renamed the building of statistics. Now it is called, PAP Moran building. Okay. Okay. Now what is said, if you want to test for dependence, spatial dependence, what you should be doing? Now we all know, Darwin-Watson test. Okay. Now we can write down the Darwin-Watson test this way. No, that's the A. But no, see, this is 1950, and Pat Moran did a test in 1948, which I call generalization of this. Even he did it before. He said, if you look at what is the ratio of the two quadratic form, and the top part is E prime A E, where you have this, structure of A. Okay. And why this is this structure? Because in Darwin-Watson test we are testing only for the first order autocorrelation. That's why you can see in A matrix, what are the non-zero elements? Diagonals are non-zero, and only the diagonal just top of it and just below it non-zero, but everything else is zero. Because of the structure of your hypothesis that you are testing first order correlation. What Moran said, why you want to, he said, he didn't talk about this. He said, anytime we can test for dependence by considering this ratio of quadratic form where W is certain null matrix. So if you take W is equal to this, you get the Darwin-Watson test. So and what is this W? His W was like the connections, how one region is connected to other region. Okay, kind of neighborhood structure. And you can think about W maybe kind of say a reciprocal of the distance between say two spots. But again, you can measure the distance in many ways. It could be geographical distance, or it could be economic distance, or it could be social distance. Suppose you're looking at, you're studying say minority, people. Then you can say these two cities are close if the percentage of minority people are the same. That I call social distance. Okay. So in that sense, you can think about, New York will be much closer to say Los Angeles, which is the other side, than say New York with say Washington DC. Okay, so that could be a kind of distance that you can think about. Okay, so you can construct the W matrix the way you want to. Okay, so this is the test he suggested, and now suppose imagine Dr. Snow had this Moran test, then he could have calculated it. Looking at the distance from the pump. You can define, that these two locations are close by if they are in the same distance of the pump. He could have done that. If he have done that, what could have got? He could have, okay, let me just go through, he could have calculated the Moran statistics, and the p-value of Moran statistics will be like, 0.00037, which is very, highly significant. Okay. Okay, so that will be the if Moran. Of course, as you can see, Dr. Snow didn't need any test statistics because it was so obvious, from his data and his information that he gathered. And what you could do, you can see like in the time series model, what you do, you run a regression yt on yt minus 1, like AR1 model, and equivalent, spatial attribution model, what will be? You say what you are saying, suppose you don't have any other exogenous variable, what you are saying that your value at the particular location is a linear combination of the value of the nearby locations. No, that's a WY. No, and the W matrix you construct yourself, and that will give you an idea about rho. Okay, and if you estimate, with this particular data, your rho had becomes almost 0.5. Okay, so you can see the dependence very clearly. Okay. I have to go a bit quickly. Okay, yeah. I think I say, this is an area is still at very infancy. But you can see the number of papers. Let us think about these 5 years, 95 to 2000, 2005, 2006. So these are the number of papers published in kind of journals, Journal Econometrics, Review of Economics and Statistics, Econometrica, Applied Econometrics, JBS. So these are kind of our mainstream econometrics journal. But if you even think about kind of this is called Journal of Real Estate Economics and Finance, they have been publishing mostly kind of pure applied work, but now the number of papers are even also going up in terms of spatial economics, general urban economics, okay, like Journal of Economic Geography. Earlier days they only have maps, no spatial econometrics, but now see, now this geographic journal is using a lot of econometric techniques, so I included those numbers only have kind of spatial econometrics there, so you can see the kind of trend that's going on, like a land economy. This is land economics, So earlier it was only pure, charts and diagrams, but now they're slowly using econometric techniques. Okay, so in that sense, it's a good area to get into, and particularly in the context of Russia. Anytime you have spatial heterogeneity, this is a good application. So sometimes you see this, data. They say, oh, Russia is growing, maybe say 2% or something, say, but that does not say anything, And if you look at this what I call say spatial heterogeneity is huge. Some parts of Russia of course is growing, but there are some parts which are not growing, maybe going, maybe have a negative growth. Like I looked into the data of Russia, found out your south part, like all those areas what you call Chechnya, Ingushetia, and all those places. The picture is completely different. Okay, and also you will see all those the areas which are not growing, they're all clustered together. It is not just one isolated. Suppose how many states, provinces you have? 83 or something in Russia. Yeah, and you can see like 10 or 12 these regions or provinces are all clustered. Either they are in the good place or in the very, very bad places. They're all clustered. Okay, so this regional, I think, divergence is very important, because you don't want to have this kind of uneven growth. You want to have as much as balanced growth, and you can see that very clearly once you do this spatial analysis. And this dependence is very, very strong. I have seen some work, I think, done by maybe in Moscow New School of Economics. There are a couple of people working on this, but not many. I think, how many papers are there on spatial econometrics in Russia? Only 4 papers. Oh, I say 4.4. 4 are available in the internet, and one person just sent me a paper yesterday, the draft of the proposal. Okay, so that's all have been done in Russian context. I mean, Russia is a huge country, and there are only 4 papers which looked into the spatial dependent structure. Like one paper looks at the growth convergence. One paper look at youth unemployment, and I think another paper look at what you call it. 2 paper looks at called income inequality. How the income inequality, and again is very. You won't imagine how much this income inequality is there in Russia, even after take account of this living cost. Even after adjust the living cost, you will see you are lucky you are in the good area. This Pittsburgh, what called St. Petersburg is the most, I think, one of the richest area in Russia. Okay, but if you look at the income structure here and then go to the Ural areas, you will see there is a huge income difference. Okay, so I think this is a very good area, not just kind of doing econometrics for the sake of econometrics, but the policy point of view and the practical point of view, I think is very interesting. Now, as I was saying, in time series things are, I won't say easy, but much simpler. So when you talk about time dependence, you say look at time t data depends only on the past, so your dependence goes on only one direction. But what I said, my spatial dependence, what I was saying, the value at location I can be written as a linear combination of the value of the neighborhood values, and wij could be 0 and 1 depending on whether they are neighbor or not, as you can see that, Now how can this be, this location can be dependent on this, but this location may not be dependent on this, but again here is a location here, but this could be dependent as far away from here. So these dependence can go all kinds of direction, okay. So that's the problem, that's why it is not very easy to model the spatial dependence, okay. And also if you look at simple ideas like this, see in time series you can write the model so many ways, in the simple autoregressive, or in terms of conditional moments, or in terms of covariance structure, they are all identical, you can go one to here, go back and forth, no problem. But if I write down my spatial model, in conditional way or in this way, they are completely different, they will have completely different implication. Okay, so because the dependence goes in so many ways, that's the crime in Columbus. Okay, so every time you go to the police department of Columbus, you will see this. They will tell you that how many. I think it's like every weekend they get this picture. Okay, and it tells you how much crimes you had. All kinds of crime, and that's why the data is very good. Okay, but what are we talking about? Not the recent data. I'll be talking about like more aggregate data, little bit kind of old data. This is like this is a Columbus, this is the basically Columbus area map, this is the putting them into 49 areas, because nobody lives like this kind of areas, there are not many people living here. Essentially this is like a highway, and similarly this part is just pure highway, so people are living mostly these areas, and then we look into the so this means darker means more crime, and all is aggregate crime, assault, theft, all kinds of things. Okay. Now you can see the clustering, and this is the kind of downtown, and university, Ohio State University is somewhere here, and you can see the crime on campus is also it's pretty high. Okay. Now suppose you want to. This is more like an illustration, not a very real applied serious work on crime. Okay. Suppose I want to explain crime, then one way to look at the income and the house. This is like a medium income. So 49 locations. In US we call it census tract, like 5 or 6 blocks are put together as a census tract. So you can run a regression on the kind of total number of crime, on the medium income of the people living at that particular location, and this is like medium house prices, and you get a nice result, pretty good result. Okay, now you can be happy with that, signs are nice. I forgot the R-square. R-square is very pretty high, even for this cross-section data. Okay. Now that's what I'm going to talk about. What I'm going to talk about. Suppose I want to think about a model including spatial dependence. Okay. So this is my possible model for spatial dependence. Okay, just a model. Then now, but I don't want to estimate. No, see, this estimation is not that straightforward, because you cannot run a OLS y on wy and x. Because this is like a more like there is a simultaneity problem, it's more like endogenous variable, you need either maximum likelihood or instrumental variable estimation to estimate rho and beta, estimate beta will get affected, it will be inconsistent, of course unbiased, if you run OLS. Okay. So you might want to test for rho is equal to 0 before you estimate this model. Again I said testing is simple, you look at the score and rho is equal to 0, and as I said, the raw score test, you will be testing a hypothesis, but the estimators will be coming from the null. Under rho is equal to 0, you can just run the OLS. So my test will be based on U tilde, which are OLS residuals. Okay, so I can do that test, and look at the test is highly significant. Okay, and then my idea is you do the test and then estimate the model only if rho is significant. Then you can see, now look at what happened. Rho hat is pretty high, and log likelihood function is much higher than before, like 170 minus 170, then you get minus 165. Not only that, look at these coefficients. Now earlier my beta 1 coefficient was 1.59. Now it is 1.04. So it's kind of earlier as if you are kind of, what I would say, you're overestimating this parameter, because once you ignore the spatial dependence, that spatial dependence will be kind of reflected through the dependence on the income. So the income coefficient will look very large, not because it is that large, but because you have ignored the spatial dependent structure. Okay, so that's the one thing. Okay, now you can be happy with this model, but there is a big problem. You can put the spatial dependence either this way through lagged variable, what we call it lag dependence, or your spatial dependence can come from indirectly through error term. Now it is a completely different model. As if you can think about this is like a autoregressive model, and this is more like a moving average model. They are completely different model. In the time series another problem. Autoregressive moving average models are very close by, but in the spatial context they have completely different implication. They are far apart. Then suppose I now want to test lambda is equal to 0 or not. In this model again we use OLS, and this test is exactly same as the Moran test I talked about, and this is also significant. And if you estimate lambda, it is highly significant. In lambda even significant, much higher than rho hat. So now you end up with another model. Then what do you do? Whether you might have dependence, one of them that may be true, or this may be true, or both may be true. Then somebody said, okay, why don't we do this? Put the model together, test them jointly. Okay, I can test them jointly. Then again, this is significant. But then you don't know which one is significant, because it says, that this is rejected. That rejected means, at least one of them is significant, but don't know which one is significant. Then let us then know, we don't know, let us estimate the whole model. Then now we can see, once you estimate the whole model, then rho hat, it keeps it significant. But now look at lambda, it is no longer significant. But we just estimated lambda before by itself, it is highly significant. And I think this happens all the time in econometrics. We look at things piece by piece. When you look at things piece by piece, everything might look significant. My idea is don't go to this step. Before I go into this step, estimating the huge model, I mean here not huge, but in many contexts it will become huge. What you should do, why this happens, see, this is what I call total amount of misspecification. You are looking at two directions and the total amount. Now what happens, these two parameters are not independent of each other. One we are saying pure direct dependence, another is saying indirect dependence, but they are interconnected. So you cannot test them kind of separately, because when we are using this test, we are testing rho is equal to 0, but assuming lambda is equal to 0. And when you are testing this, we are testing lambda is equal to 0, but assuming rho is equal to 0. So that's why both look significant. But what I said, then what you could do, I do not want to estimate a model without knowing which direction we need to go. And here is the idea that I to kind of tell you, yeah, that's what I said, we can do this, but okay, let me go this. Okay, okay, that's what I do. See, all the tests are based on the score function. My score function I always say, in this way. So d rho is the score function of rho, d lambda is the score function. We should not do just d rho, d lambda. What we should do, when I am talking about the score of rho, I should subtract from d rho the effect of d lambda. It's like the way we do with run regression. We always know that when you do the OLS, see, OLS is nothing but, that's what I tell my student, is nothing but decomposing your value of y into two parts. Error, and of course you have the x beta hat. And we know your prediction is always orthogonal to the error term, and that's what it is. You make them orthogonal. Earlier d rho d lambda is not orthogonal. So what we do from the d rho you subtract the expected value of d rho and d lambda. Then what happens? I call it a net score, d rho star, and this d rho star by construction will be orthogonal to d lambda. Just like we have y minus x beta hat is orthogonal to x. So your error term becomes automatically orthogonal to the predictor. Now instead of RS rho, we can do our test based on d rho star. That's what I call orthogonalize, or sorry, the adjusted test. Okay. Now again it can be calculated very simple way. Now look at it. If you remember, my RS rho was pretty high, like 9 point something. Let me go to 9.36. Now out of this RS rho, if I take the effect of lambda away, how much I am left? It is only 3.72, but it is still significant. And if you use the real likelihood ratio test, likelihood ratio test means you have to estimate everything. It is very close. It is still significant. So what it says, that means even after I take account of this, indirect effect, of lambda, my rho is still significant. But now look at what happens in the lambda. You can do the same thing. From d lambda, get rid of the effect of rho. Then look at the, what I call, adjusted test. There is no effect anymore. But my earlier lambda hat was highly significant, and also this RS lambda also was significant, but now after I take account of rho, this is no longer significant. Basically now I have removed the effect of rho. Okay. So that means after I do all those things, basically it says these two tests, when you use this adjusted test, it tells you there is no need to look at lambda anymore, just only consider them just estimate rho only. Now you can put all of them together, that's the way it is, So what I will be doing, I will be doing OLS estimation, then doing the testing, then I don't know, then after we do the test, it says there is no need to estimate this model at all, or even there is no need to estimate this at all. No, because we know only lambda is significant, so I will just do this and then just do this, and then we'll get the estimate of rho. So this will be my kind of final model without talking about anything like this. Okay. Now look at what happened. See, this model is good enough. And so I have seen a lot of paper with the same data. They said this is right, and some people say this is right. Because you look at them separately, of course, both look equally right. Okay. But you can do this. I'm not saying that you cannot do this, but this requires a lot more effort. You have to estimate both rho and lambda to know whether it's significant or not. Okay, there is no need to estimate a huge model. Just do OLS and test whether this is 0 or not, taking account of the possible presence of lambda. Okay, so that's what I was going to talk about. Okay, let me kind of maybe I should stop 5 minutes. Yeah, okay, 5 minutes. Yeah, okay. Now let us go into kind of little bit more model, where estimation, this is the model I was talking about. In fact, I just come to my seminar topic. Testing spatial panel model. Okay, 5 minutes. Okay. Now, but as I said, how model can go wrong? See, here these are the things, but it could go wrong many more than that. See, here I have partial dependence. Here I have the individual effect. Here I have the lag dependence. Here I have serial correlation. So now we are looking at 4 different directions. One is the spatial dependence, both in terms of lag and error, or non-spatial things like serial correlation and lag effect. Okay. Now in this case, what we will be doing? We will do the following. All this, forget about the math. Maybe we will do this one. Test the whole thing together. See whether any one of them is, or at least one of them is significant, and then test like this. Okay. So I will do only 5 tests at a low significance level, say 1%. Okay. That means my maximum significance level will be 5%. Okay. So I will test this, but taking account of all the 3 parameters. Okay, taking account of all the 3 parameters, and I use this for the convergence, for the, say, let me forget about this, all the stuff there. I use this for the data for like 91 countries where we will talk about growth convergence. See what happened, my total is highly significant. See, I am testing whether, so this will be my total amount of misspecification. That means it says at least one of the 3 are at least one of them are significant. Now the question is, how do you know which one is significant? So I do this one test, and then I just go to the adjusted test. Now look at this, unadjusted test is always higher than the adjusted test. Okay? So in some sense, what we are doing, we are decomposing this total amount of misspecification into 4 orthogonal components by looking at the adjusted test. Okay? Now the most interesting one is this one. It says, unadjusted test, this is highly significant, but once you eliminate the effect of rest of the parameters, it's no longer significant. So basically, it gives you very quickly, and also it tells you, what the most important part of this model, or what is the most amount of misspecification can be coming through. It will be coming through mostly from the heterogeneity. Not much of spatial dependence, even this one, it look huge, but once you take account of rest of them, it from 32.31, it comes to only 6.36. Similarly, look at the this one, yeah, this is still significant, but from 30 it becomes, this is the lag dependence, and the error dependence, nothing left, and time series correlation, it is, the net effect is 6.36, significant but not much. But now look at this one, out of 220 total misspecification, heterogeneity counts for huge part, like a 70%. So that means, if you really want to model, first thing what you should try to do, forget about the spatial dependence or time series dependence. You should look at the heterogeneity. I mean, that's natural. You if you go to 91 countries, I mean, it is hard to say how these countries will be similar. I always say, best example of heterogeneity, look at Canada, United States and Mexico. Look at Mexico and United States. I don't think there is any example of 2 countries are neighbor and they have so much economic difference. And I tell my students, those who come from Mexico, I said, Mexico is a lucky country, so close to US, and Mexico is an unlucky country, so close to US. Okay, so I think I'll stop there. Okay.
Thanks so much.
Yeah.
Questions, please.
Okay, sure.
Basically, so like it's not about the tests, but
Yeah.
more like about the methodologies.
Yeah.
Did you say, did I understand correctly that literally you can use the approach literally to everything? I mean, it depends how you define the distance, and then
Exactly.
you can just get it to this.
Exactly, like going back to the finance data, suppose you're looking at the distance between, say, 2 stocks or 2 companies, you can look at kind of, their kind of, capital structure, or whether they have a common CEOs. I mean, we have all those publicly available lot of data set, and it doesn't have to be only one thing. It could be a combination of many things. Yeah, so it would be, but again, it is subjective, because you can construct W matrix many ways, but sometimes I say, you do the analysis with many Ws. And one good case I will say this, the crime data, or also with this data, we have done the W in 2-3 different ways, but the results are very similar. No matter, sometimes you can think about this, say neighbor, if you have only common border, just give 0, 1. As W matrix, but also you can think about, don't give 0 and 1, you look at the kind of share of the border. Suppose you have 4 neighbor, but they may not have same amount of common border. So you give the highest to it, the one which has higher. Like I always tell, Russia is the best example doing spatial analysis, because they have the largest number of neighbors, 14 I think. Some are good, some are bad, of course. Okay, so I think that's a good way of doing the, and I mean that's a 15 point you have in terms of location. You can see the effect of Russia on them and effect of them on Russia, and you will see Russia of course dominates. Okay, I think Belarus, kind of small ones. I don't think they have any effect on Putin, and how much Putin has effect on them. Okay. So it's a good place, you have a heterogeneity, you have dependence, and then I think,
Are those 4 people in Russia?
Pardon?
That, like those 4 people who are doing spatial econometrics in Russia, are they all based in Moscow?
Oh no, let me see. Moscow, I'm going to see her tomorrow or on Monday. Her name is Olga Dimiedova. You might know, no? Okay. Yeah, all in Moscow. Either New School
Yeah, or
Oh.
high school economics.
High school economics, but some are outside US. I think most of them have co-author in Germany. I think I can imagine, like collaboration. So they have the data, and this German institute have the technique or computer package.
Yeah.
They get together. Yeah. I think all are joint papers. All are joint papers. Yeah. So that's the way I think they have been, working on. But again, still very primitive stage. I mean, 4 papers. I think only one of them is published so far. And other 3 are kind of, available online, but discussion paper. Other paper is what I call work in progress.
Yeah.
UC under construction. Okay, thank you very much. Yeah, thank you very much. Yeah.